Hey, it's Mr. Shrum. Welcome back to a physical science tutorial. And today we're going to look at models of the atom. So we're going to try to describe the experimental basis for the atom and identify the parts of the atom. So for an introduction, consider a granola bar and you cut it in half. Then you cut one of the pieces in half and so on. How many times can you keep cutting pieces in half? In fact, there will come a point when you can't physically cut it up any further. And that is true even if you replace the bar with any other object. And why is that? Why is there a physical limitation to how small we can cut something up? For centuries, scientists have been fascinated with the study of matter. Their constant search to discover the smallest indivisible part of an object led to the discovery of atoms. Early scientists didn't have modern equipment. They relied on gold foils, glass tubes, metal plates, and other such items to imagine the shape and structure of an atom. So here we're given a timeline of atomic theory. Modern atomic theory evolved from the contributions of different scientists over many years. It's very rare that one scientist just comes out of nowhere and revolutionizes the theory. Theories are built on previous knowledge and work, and some of them are based on, they base the structure of the atom purely on their imagination, and others conducted experiments to formulate their theories. So here we can click on each event in the timeline and learn a bit about the contributions these scientists made and what led to the modern atomic theory. So here we go. So around 400 BC, Democritus, he was an ancient Greek philosopher, and he was the first to propose the theory of atoms. He observed the objects could be divided into smaller and smaller pieces until one reached a point where each piece couldn't be divided any further. So, with that information, he concluded that all matter is made up of small particles that are indivisible and indestructible. And he named these particles atoms. Democritus also believed that these atoms of different substances were distinct from each other, and that the shape of the atoms defined the properties of a substance. Later, we have in 1803 John Dalton. He was an English physicist and chemist born in 1766. He's regarded as the father of modern atomic theory. Dalton's atomic theory was based on the law of conservation of mass and the law of definite proportions proposed by scientists before him. His theory supported Democritus's idea of an indivisible atom. He stated that atoms were spherical. Atoms of different elements had different weights, and they combined in whole number ratios to form compounds. Dalton's theory was widely accepted at the time because it was backed by scientific evidence. Then we have, more than 90 years later, J Thompson. He studied physics and mathematics at Cambridge University, and he was the first to discover the existence of electrons. While he was experimenting with cathode ray tubes, he observed that a cathode ray was deflected toward the positively charged electric plates. So he concluded that a cathode ray was made up of negatively charged subatomic particles, and those particles were later named electrons. Later on, Thomson proposed his plum pudding model of an atom in which electrons are stuck in a cloud of positively charged matter. So here's an example of that. This was his theory. You just had this big cloud of positively charged matter, and then within that, there would be sprinkled like plums and pudding, which was, I guess, popular at the time. But not very much later, 14, 15 years or so, Ernest Rutherford, a physicist from New Zealand, near Australia, became Thomson's student at Cambridge University, and he discovered that the mass of an atom is concentrated in its nucleus. In an experiment designed to test Thomson's plum pudding atomic model, Rutherford bombarded a thin gold foil with positively charged particles. They were called alpha particles. And his observations led him to conclude that the mass of an atom is concentrated at its center, or nucleus. And the nucleus is positively charged, and the electrons revolving around it in an empty space, kind of like this model. So you have the nucleus, and then the electrons are kind of rotating around, spinning around the positively charged nucleus. 2 years later, we have Niels Bohr. He was a Danish physicist, and he took Rutherford's atomic model and refined it, because Rutherford's model couldn't explain why the electrons didn't fall into the positively charged nucleus. If you remember from our magnetism lessons, positive and negative attracts, right? So if the nucleus is positive and the electron is negative, why don't they attract each other and fall into one another? Well, Bohr proposed a planetary model of the atom wherein electrons revolve in circular orbits at fixed distances from the nucleus. And according to Bohr, electrons from one orbit move to a higher orbit by absorbing energy. When these electrons moved back to a lower orbit, they emitted light energy. So they were moved to a higher energetic state, and then when they lowered to a lower energy state, they emitted some light energy. And this theory formed the basis for the modern atomic theory. And more than 10 years later, we have Erwin Schrodinger. He was an Austrian physicist, and he developed a mathematical equation to define the probability of finding an electron around the nucleus. So earlier, it was believed that electrons were particles that moved in circular orbits around the nucleus. But Louis de Broglie, a French physicist, found that electrons showed the properties of both particles and waves. Based on this idea, Schrodinger developed an atomic model that incorporated both the particle and wave-like nature of the electrons. His model showed the location of electrons around the nucleus as a density cloud. So this is the latest model, well, not the latest, but the latest on this timeline, where you have the nucleus, and then you have electrons around the nucleus in this cloud, where some places have more electrons than other places. Some are more dense with electrons. So what do we know about the atom? Let's look at this video.
Copper and tin are made up of particles called atoms. In pure copper, all the atoms are the same as each other. It's the same with tin, but tin atoms are bigger. A pure element is made of just one type of atom. The idea of the atom goes back as far as the ancient Greek philosophers. Democritus was one of the first to think that everything was made of particles. As he looked at a pile of sand, he could see it was made of grains. Democritus thought that if you could look close up and actually see inside any substance, you'd find that it too was made of tiny particles. If you take a piece of cheese and cut it in half and then in half again and keep on cutting, eventually you'll be left with a tiny grain of cheese. Your knife isn't delicate enough to cut it any further. But Democritus imagined that you could keep on cutting. He decided that you would eventually get to a point beyond which it couldn't be divided anymore. Atomos is Greek for not cuttable, so Democritus called the smallest unit of matter the atom. Back then, he had no way of proving whether atoms existed, but today, high-tech machines allow us to see them. A layer of aluminium gives this CD its silvery sheen. But at greater and greater magnification, it looks quite different. Keep on magnifying the image thousands and thousands of times, and eventually you can see the individual aluminium atoms. So, just how small is an atom? Imagine building a pile of CDs as high as you can. Just think how many you would need to build a pile 9 kilometers high, as tall as Mount Everest. Well, that's the same as the number of atoms in the height of just one CD. Nearly 9 million.
Okay. So back to Democritus, the ancient Greek philosopher that first suggested the existence of atoms. So he studied how objects could be cut into tiny pieces, and he could just keep going. According to Democritus, atoms were the building blocks of matter, and they were indestructible, indivisible. He believed that atoms had different shapes and sizes and were responsible for different properties of matter. He imagined that white objects were made of smooth atoms, while black ones were made of rough atoms. Unfortunately, his ideas lacked evidence and were rejected by Aristotle, who was one of the most influential philosophers of his time. However, another scientist, John Dalton, backed Democritus's ideas almost 2,000 years later. So, unlike Democritus, Dalton used scientific methods to explain his atomic theory. He wanted to find out how materials transformed during a chemical change and why such changes were accompanied by a change in energy. So he studied how gases combined with each other to form compounds. He based his research on the works of two well-known scientists of his time, Antoine Lavoisier and Joseph Proust. Let me see if I'm pronouncing the French one correctly. I've seen his name in print, but not aloud in a while.
Lavoisier and Joseph Proust.
Yeah, there you go.
Lavoisier, a French chemist.
Lavoisier. Antoine Lavoisier and Joseph Proust. So Lavoisier, he was a French chemist. He had proposed the law of conservation of mass. In his experiments, he observed that the mass of materials remained constant during a chemical change. This led him to believe that matter is neither created nor destroyed during a chemical change. It is simply transformed. Proust, another French chemist, observed that the elements in a chemical compound always combine in the same proportion. So, for example, common salt, sodium chloride, would always have sodium and chlorine in the same proportion, no matter where the sample is taken from. This observation led to the law of definite proportions. And he based his atomic theory on the findings of Lavoisier and Proust, as well as his own experiments. So you'll see that in science a lot. Scientists will look back, look at what people have done with their experiments, and then take that knowledge and use it in their own experiments. And in his theory, Dalton stated that all elements are made up of tiny, solid, spherical particles called atoms, which are indivisible and indestructible. The atoms of a given element are similar, but differ from atoms of other elements. Atoms of different elements combine in whole number ratios to form compounds. When atoms separate, combine, or rearrange, chemical reactions occur. But these reactions don't change the atoms of one element into those of any other element. Later, we talk about Thomson, whereas Dalton's hypothesis of a solid spherical indivisible atom was proved wrong when J Thompson discovered the electron. Thomson was conducting experiments with cathode rays when he made his discovery. He sealed gases in these glass tubes fitted with electrodes on both sides, and you can see that here. He connected the electrodes to a source of electricity. One electrode, called an anode, became positively charged, and the other, called a cathode, became negatively charged. When he passed an electric current through the electrodes, a glowing beam traveled from the cathode to the anode, and that beam is called a cathode ray. Thomson observed that a cathode ray is deflected when it passes through an electrical or magnetic field. So we have this cathode ray, and it deflects towards the positive end. Thomson used a pair of electrically charged plates and found that the rays deflected towards the positively charged plate. Because opposite charges attract, he concluded that a cathode ray is made up of negatively charged particles, and he called them corpuscles. These particles were later called electrons, which are way cooler sounding. Thomson conducted another experiment to measure the ratio of the charge of an electron and its mass. He found that the ratio didn't change no matter which gas he used in the tube or the metal he used for the electrodes. So he discovered that this was a consistent phenomena. And this discovery led him to conclude that electrons are parts of the atoms of all elements. And his findings suggested that atoms contain negatively charged electrons. But he also knew that atoms were overall electrically neutral. As this fact contradicted his findings, Thomson concluded the atoms had some degree of positive charge to cancel out the negative charge. And to explain the neutrality of an atom, he proposed his own model, which is nicknamed the plum pudding model. According to Thomson's model, electrons are stuck in a cloud of positively charged particles called protons. He visualized the electrons as raisins stuck in a dense fruit cake, and the English call this plum pudding. So that's where that name came from. And then later we had Rutherford. He took Thomson's atomic model and proved it wrong, or less accurate than reality. And he was a former student of Thomson. So he performed his gold foil experiment to test the plum pudding theory. He bombarded a thin foil of gold with alpha particles. He expected the alpha particles to pass through the gold foil with minor deflections. However, that is not what happened. He observed that most alpha particles passed right through the foil, while some were deflected at large angles. And what was surprising to Rutherford most was that a few particles even bounced back to their source, like this one. Wham, bam, and wham, bam. So after carefully considering the results of this experiment, Rutherford concluded that the mass and the positive charge of an atom are highly concentrated near the center. When the alpha particles are aimed directly at the atom's center, they bounce straight back to the source. So alpha particles will pass through the electron cloud, but when it hits that positively charged nucleus, it'll bounce back or deflect. So, based on what he saw, Rutherford suggested a new atomic model. And in this one, the mass of the atom is concentrated in a small region at the center, the nucleus, and it contains positively charged particles called protons and neutrally charged particles called neutrons. And the rest of the atom is empty space in which electrons move around the nucleus in the same way that planets revolve around the sun. So that was his model. And for that reason, it's called the planetary model or the nuclear atom. Rutherford's model had a flaw. If the negatively charged particles or negatively charged electrons move around the positively charged nucleus, theoretically, they should give off energy and eventually fall into that nucleus. So the main question this model did not answer was, what keeps the electrons from falling into that nucleus? And that brings us to Niels Bohr. He was Danish, and he modified Rutherford's planetary model. According to Bohr's atomic model, electrons do not fall into the nucleus because they move in specific paths or orbits without absorbing or emitting energy. And each orbit has a fixed energy level. And based on the distance of the orbit from the nucleus, electrons with less energy move in orbits that are closer to the nucleus, and those with more energy move in orbits that are further out from the nucleus. An electron moving in a lower energy level near the nucleus can jump to a higher energy level if it gains enough energy. And the specific amount of energy needed to make this transition is called a quantum. An electron usually doesn't remain long at this high energy. It will drop back to a lower level by releasing a quantum of light energy called a photon. Bohr's atomic model formed the first quantum theory of atoms, since this model is a modification of Rutherford's model. It's also known as the Rutherford-Bohr model. And although his quantum theory provided a much better explanation of atomic structure, scientists were still unable to trace the exact path of an electron. Louis de Broglie A French physicist proposed that electrons behave like particles and waves. He, along with other scientists, bombarded metal surfaces with electrons. They observed that the reflected electrons produce wave-like patterns similar to X-rays. So de Broglie concluded that electrons, which were believed to be particles, also had wave-like characteristics. And he suggested that these waves spread into specific regions outside the nucleus. And based on that hypothesis of de Broglie's, Erwin Schrodinger developed a mathematical equation describing the path of electrons and specific energy levels in terms of probability. The probable location of electrons around the nucleus form an electron cloud. Denser regions in the cloud indicate higher probability, so it's more likely that electrons will be found there. If it's less dense, there's a lower chance that you will find electrons there. And his work was the culmination of modern atomic models. And this model was known as the quantum mechanical model. And I'll stop right there today, and we'll pick up again right where we left off and finish this lesson. But until then, have a great day, and I will see you all later. Bye-bye.